Okay, let's look into trig functions of a complex variable. Section 334. So we haven't actually defined sines and cosines as functions of a complex variable yet. So let's run through this section. There's a lot of little algebraic manipulations that aren't terribly enlightening. But there's some necessary stuff to show that we get analytic functions when we deal with sines and cosines, and largely analytic functions when we deal with the other trig functions. So plan is to define all 6 trig functions and explore some of their properties. In this setting of the complex realm, it turns out these functions are going to be related to, no surprise, the regular old real trig functions. And also the hyperbolic trig functions pop up in a number of ways. So where we currently stand is we've defined the exponential function e to the z in terms of the real exponential function in sines and cosines of the imaginary part, cosine y plus I sine y. So there's definitely trig functions lurking somewhere inside these exponential functions. In fact, we can extract them by using the fact that Euler's formula states that e to the ix, shifting variables to x, is cosine x plus I sine x. E to the negative ix, which we know to be the conjugate of e to the ix from some previous stuff, is cosine x minus I sine x, conjugating the right-hand side, or replacing x with negative x and using even and oddness of sines and cosines. But we can solve for cosine x from these 2 pieces of information, add these 2 together, the imaginary parts, the sine function parts will cancel out, leaving us with the cosine part, usually 2 cosines. So we'll divide by 2, and we can express the cosine of x in terms of exponential functions involving purely imaginary numbers, e to the ix and e to the negative ix. And similarly, we could take a difference and solve for sine x in terms of e to the ix and e to the negative ix. So this motivates the following. So we're going to mimic this, except we're going to replace the x with the parameter z and define cosine z and sine z in terms of the well-established exponential function of a complex variable. So we can define functions however we like. These will be entire functions because the exponential function is an entire function. Of course, we got no right calling them sines and cosines unless they behave like sines and cosines. And we see from the observation above, if we'll take z to be real, z equal to x, both of these equations reduce down to the previous equations. And so we must be on the right track. These agree with sines and cosines in terms of x being real. In addition, we know how to differentiate exponential functions. So we can take derivatives. The derivative of cosine, here's the expression we had for cosine, piece of cake to differentiate, a little bit of chain rule stuff because of the exponentials. And sure enough, we get that the derivative of cosine x is negative sine x. Similarly, the derivative of sine x, sine z, I should say, is cosine z. So sine z, cosine z differentiate in analogous ways that sines and cosines differentiate. So we must be on the right track. We can also observe from these definitions of sines and cosines in terms of exponentials that sine negative z is the same as sine z, cosine negative z is the same as cosine z. So these sine functions, I always say, are spitting out these negative signs, that is, they're odd functions. And the cosine function is absorbing negatives, that is, the cosine function is an even function. And let's try that again. We also have the identity e to the iz equals cosine z plus I sine z. We can establish that by adding appropriately these exponential functions, which is kind of a glorified version of Euler's formula. If z is real, it is Euler's formula. But this holds as well for z complex. There are, like I said, there's a lot of algebraic stuff here. There's summation formulas for sines and cosines. These are to be verified in some of the exercises. The usual summation formula for cosine z1 plus z2, is familiar from what you have from the real setting. Summation formula, sine z1 plus z2, familiar as well. We could get difference formulas from these as well, using our knowledge about sines and cosines in the complex setting as even and odd functions, as explained above. From the summation formulas, we can get double angle formulas, same thing we had in the real setting. The summation formulas let us establish cofunction relationships. Did you ever wonder who put the co in cosine? The reason these are called cofunctions is because complementary angles and cofunctions yield the same values. That's the reason cosine is called cosine instead of something else. If I plug an angle z into the sine function and I plug in an angle complementary to it in the cosine function, we'll get equality. Here the statement is cosine z plus pi halves equals sine z plus pi halves equals cosine z, confirmed from these summation formulas. This isn't precisely the cofunction relationship, but it's intimately related to it. We could state it if we had some differences up here, sine and cosine of z1 minus z2. But that's the reason cofunctions are called cofunctions, and those relationships hold in the complex setting also. The Pythagorean theorem can be stated as cosine squared plus sine squared equals 1 in the real setting. That identity holds in the complex setting as well, easily verified from our definitions of sines and cosines. We have periodic behavior, as always. The cosine of z plus 2 pi is the same as the cosine of z. Sine of z plus 2 pi is the same as sine of z, confirmed by those summation formulas. So there's the periodic behavior of sines and cosines. They have a real period of 2 pi. Phase shift properties, if I'll shift a cosine function by pi units, pi radians, we'll get negative cosine z. Shift a sine function by pi units, you get a negative sine z, negative sine x in the real setting. Usual properties from the reals, so no surprises there. There's a bit of a surprise. We're going to drag the hyperbolic trig functions in. And probably these in your past experience have largely been overlooked. They're going to play a role here that pop up in terms of, when we look at moduli of sines and cosines. These hyperbolic trig functions are going to come out of nowhere. And I guess it isn't totally surprising because you'll recall, or FYI, the definition of cosh y, hyperbolic cosine of y, is e to the y plus e to the negative y over 2. Sinh, hyperbolic sine of y, is e to the y minus e to the negative y over 2. And it looks a lot like what we had upstairs for sines and cosines in terms of complex numbers. It isn't. There's nothing complex in any of this hyperbolic definition stuff. It's all real. But the exponential functions seem to play some similar role here as they played upstairs when we define sines and cosines in terms of exponentials. We can relate sines and cosines with coshes and sinh as follows for those reasons. If we'll take the cosine of iy, okay, here's our definition of cosine in terms of exponential functions with z replaced with iy, and these imaginary numbers, these i's get together and we lose the imaginary stuff. We're left with some real stuff, and out pops from cosine iy, out pops a hyperbolic cosine, cosh y, and you see the definition of it up here at the top of the screen. Similarly, sine iy, follow your nose from the definition, will lead you to I sinh y. Here's the statement, here's the sinh function. And there seems to be some differences in some negative signs here, but what's happened is 1 over I equals negative I. So take this I, move it to the numerator, throw in a negative sign. You'll in fact get I sinh y out of this right-hand side. The real and imaginary parts, is stated as a lemma, of cosine z and sine z can be expressed in terms of sines and cosines, sinh and cosh as follows. So if we wanted really to explicitly see if these were analytic functions using the Cauchy-Riemann equations, this would be useful. We know these are sums or differences of analytic functions because the exponential function is analytic. So we've already got those bases covered. But this does allow us to write real part of sine z in terms of sine x and cosh y, imaginary part of sine z in terms of cosine x and sinh y, similar type relationships for cosine of z. Let's take a look at the computations for that. It's just straightforward computations. So it's, as a consequence, not terribly enlightening. I mean, the result's cute because I get to explicitly grab hold of the real and imaginary parts of these functions. Well, let's let z1 be x and z2 be iy and use the summation formula. Then if we wish to consider the sine of z, that is the sine of x plus iy, we'll treat z1 as x, z2 as iz. So we've got a summation formula when the input arguments are complex numbers, as the iy is. So we'll substitute those into that summation formula. It'll produce something of this sort, substituting z1 equals x, z2 equals y, produces these parts here. We just saw above that the cosine of iy is the same as cosh of y, and the sine of iy is the same as I sinh y, as the previous two little identities. So we can modify this cosine iy to cosh y, this sine iy to I sinh y, making those substitutions. We get the sine of z equals sine x cosh y plus I cosine x sinh y. There's your real part of sine z, is claimed up here, and here's the imaginary part of sine z. We could do a similar type thing for cosine of z to extract this second relationship using the summation formulas, taking kind of a slightly different approach to it. We're going to differentiate the sine function, since we have it expressed in terms of these real and imaginary parts. We know how to calculate derivatives in terms of partial derivatives based on some of the results back when we were doing Cauchy-Riemann equations. So cosine of z is a derivative of sine z that we established earlier. We can take the derivative of an analytic function by taking the partial of the real part with respect to x plus I partial of the imaginary part with respect to x as well. I guess that was theorem 2.21.a. So we'll take partial derivatives. We had sine z expressed earlier from the previous slide. So this will be a partial with respect to x of sine x cosh y and a partial with respect to x of cosine x sinh y. With respect to x, the derivative of the sine becomes a cosine. The derivative of the cosine becomes a negative sine. The hyperbolic trig functions, not functions of x, so not relevant here. And we get the cosine of z expressed in this form, and that was the claim about cosine z. So maybe not very enamored with hyperbolic trig functions, but they do pop up. Here's a kind of, I think it's a natural way they pop up in terms of real and imaginary parts of sines and cosines in the complex realm. Let's look at moduli. When we look at moduli of analytic functions in the future, we're going to see some surprising behavior in contrast to how functions of a real variable behave. So let's take the modulus of z squared. We know the real part and the imaginary part. So we'll take the real part squared plus the imaginary part squared. We're about to use some trig identities. Good news here, everything's real once we evaluate that modulus. So we've got a sine squared cos squared plus cos squared sinh squared with x's and y's in the appropriate places. Okay, let's see, we've got a, let's take this cosine squared and replace it with 1 minus sine squared. Like I said, these are algebraic manipulations. They're easy enough to follow where they come from, what motivated them. In hindsight, we'll make some observations. So let's take the cosine squared and write that as 1 minus sine squared. Then I see a sine squared term here and a sine squared term here. We'll collect those together. Here we've got sine squared times cos squared of y. Here we've got sine squared times sinh squared of y. So we'll collect those together. That leaves us with a plus sinh squared from that term. You will recall, well, let's recall, cos squared y minus sinh squared y equals 1. That's sort of the Pythagorean theorem for hyperbolic trig functions. There's a negative sign involved. Cos squared minus sinh squared equals 1, which is what we have here. So we can replace that with 1, and we get mod sine z squared equals sinh squared x plus, sine squared x plus sinh squared y. Now, fine, there's the modulus of sine z squared. We will make some observations about this shortly. So we'll come back to that. Let's go ahead and do cosine. Similarly, I won't bore you with the details, they're just not that enlightening. If we do cosine z modulus of squared, we've got the real part, we've got the imaginary part, similar substitution, similar rearrangement, similar identity. Now we get cosine squared x plus sinh squared y. Now, these hyperbolic trig functions, sinh function, as we had a sinh squared y in both of these. So both of these involved a sinh squared y. One involved a cosine squared x and the other involved a sine squared x. But we pick up this part, must be the contribution to the imaginary part to the modulus. But this sinh function, sinh y, recall, is defined as e to the y minus e to the negative y over 2. So a funny thing happens when y approaches infinity. As y approaches infinity, this exponential function gets huge. This exponential function goes to 0. So anyhow, that sinh function grows as an exponential function. So that tells you that the cosine of z function, cosine of mod z, grows exponentially in a certain direction. That direction is along the imaginary axis. So we can make the modulus of cosine z squared and sine z squared similarly as large as we want. Now that's weird, given your experience with trig functions of a real variable where you're used to sines and cosines just oscillating between -1 and 1. They do, these do, if you restrict yourself to real inputs. But you allow the imaginary numbers to come in, and as wild, sine and cosine are unbounded functions in the complex setting. There's a reason for that. In fact, all nice analytic functions, all entire functions in the complex setting are unbounded unless they're constant functions. That's called Louisville's theorem. So there are no bounded functions except for constant functions defined in the whole complex plane, analytic in the whole complex plane. No constant functions, but, no bounded functions, but constant functions in the complex setting, which is just totally unfamiliar. You're used to sine and cosine. Hey, they're analytic, they're differentiable everywhere, they got power series representations, and they're bounded between -1 and 1 in the real setting, not true in the complex setting. We'll actually prove the fundamental theorem of algebra, time permitting, using Louisville's theorem down the road. A zero of a function is simply an input value that makes the function 0. The term root is commonly used when we're dealing with polynomial functions. Some people use the word 0 in connection with polynomial functions as well. One of my areas of complex analysis research is locating zeros of functions of a complex variable or zeros of a polynomial even by putting certain constraints on coefficients of the polynomial. But let's take a look at zeros of sines and cosines. Lemma 3.34b says the only zeros of sine z are the real zeros, z equals n pi. The only zeros of cosine z are the real zeros, pi halves plus n pi. So the only place sine and cosine are 0 as functions of a complex variable is the same place they're 0 as functions of a real variable. Let's take a quick look at that. Okay, claim is a claim of zeros of these functions. Certainly, when we input real variables, we'll get all those usual real zeros. The question is, why don't you get any other zeros? So suppose we take z equals x plus iy, and suppose that's a 0 of sine z. Well, the only time we get 0 for a complex number is when its modulus is 0. So that will imply the modulus of sine z equals 0, or more conveniently, the modulus squared of sine z equals 0. And we know how to express the modulus of sine z squared. It was sine squared x plus sinh squared y. But remember, the sinh function is given by this difference of exponential functions. And the only time the sinh function is 0 is when y is 0. Y equals 0, this term becomes 1, this term becomes 1, the expression becomes 0. For y greater than 0, this piece is larger than this piece. For y less than 0, this piece is greater than that piece. In other words, we ain't getting 0 out except when y equals 0 for the sinh function. So the only time we're getting 0 out is when y is 0. That's when the input x plus iy was actually real, and we're back to only those real zeros. The only time sine z equals 0 is when sine x equals 0. And that occurs when the input for a sine function is integer multiples of pi. For the cosine function, we'll use a little summation formula trick, though we could do a similar analysis to what we just saw. We'll take, let's take sine z minus pi halves negative. That's from the summation formula for sine, that's negative quantity, sine z cosine negative pi halves plus cosine z sine negative pi halves. Well, I know the cosine of negative pi halves is 0. I know the sine of negative pi halves is -1, so we'll evaluate those. We lose this term. We're left with negative when I distribute. I'm missing some parentheses here. When I distribute, we were left with cosine z. So cosine z equals this negative sine z minus pi halves. So the only time cosine z is 0 is when this sine function is 0, and we know when that occurs by the first part. That occurs only when that input to that sine function is an integer multiple of pi. That is when z minus pi halves equals n times pi in an integer. We'll move that pi halves to the other side of the equation, and we get z equals pi halves plus n pi. And there's your zeros of the cosine function. Same thing you had when we were dealing with real functions. Back to the notes. Like I said, this is just a hodgepodge of almost trivia in terms of zeros. And the interesting thing, I think, was the unboundedness of the modulus of sine and cosine. We could define the other 6 trig functions now of z, same way we define them in the real setting. Tangent, cotangent, secant, and cosecant. So there you go. Let's not really dwell on that too much. We might play with sine z and cosine z a little bit, probably not so much these other trig functions. None of these are entire functions. You know, you've got zeros of the sine and cosine. So that's going to indicate points at which the quotient is undefined. Where the function's undefined, it certainly isn't analytic. So these other four trig functions, unlike sine of c and cosine of c, these aren't entire functions. We know exactly where they're undefined, except where we get division by zero. They are analytic, but there are those points, and those points keep them from being entire functions. We can differentiate, and guess what? Derivative of tangent is secant squared. Derivative of cotangent is negative cosecant squared. Derivative of secant is secant tangent. Derivative of cosecant is negative cosecant cotangent of z throughout. How are you going to show that? Same way you do in calculus 2. We've got these as the definitions. You good at differentiating? You're excellent at differentiating. And these are just quotients. So we'd have to use the quotient rule. We know how to differentiate sines and cosines, same way as in the real setting. And that's the reason we're getting the same derivatives in the complex setting as we got for derivatives in the real setting. So that takes care of that sort of little clerical bit of work. And we've got the trig functions defined, and we've got some of the properties of the trig functions. Have a nice day.